Hello, everybody. Really excited to be here. Good afternoon, all. So I'm Hari, hardware architect at Pure. As Stephen mentioned, the FlashBlade has been quite a journey. I've been privileged to be part of it right from the inception. We've spoken with many of you over the years at our conferences or other sessions such as Tech Field Day about how our products are doing. So it's really exciting to be here today to talk to you about how we're accelerating AI adoption. So I'm joined today with my colleagues Boris and Robert, who are at the back. So for those of you listening online, I invite you to listen to all three sections. In this first segment, I'm going to be talking about FlashBlade, which is an all-flash scale-out file and object platform built by Pure that serves as storage for high-performance tasks such as AI. So we're going to talk a little bit about how we see the needs of AI playing on the storage industry, what sort of interfaces, what sort of attributes are required from the storage, how that ties into our design philosophies at Pure. And then we'll go a little deeper into, well, how do we make all of this work from the media up? We spend an inordinate amount of our energy focusing on how we extract maximum utility from flash media in order to enable extremely performant, extremely power efficient, space efficient technology. So we'll tie all of that together. In our future sections that Boris and Robert will present, we'll do a deeper dive into how a distributed architecture enables the performance needs for AI, and then finally tie that all together with real-world applications. So again, for those of you online, I invite you to listen to all of our sections. So we've been honored at Pure to support many hundreds, thousands of the world's AI projects. So personally, I've worked with small companies, SMBs, small research institutes that are trying to get started with AI, all the way to some of the largest companies. We've been involved with Meta in building their research supercluster. Back before AI was the buzzword that it's become over the last 18 months, it's been really exciting to see how this industry has transformed. 6 to 7 years ago, we were doing a lot of work on CNNs, convolutional neural networks. We were working with images, and there was a lot of ADAS work happening. About 18 months ago, a ton of that shifted over to, well, it's all text-based, it's LLMs. You could fit all of Wikipedia within, 5 terabytes of storage or so. So the needs of storage changed quite rapidly, right? You went from these large images to, you need a ton of performance to keep your GPUs fed, but you have perhaps relatively modest quantums of data. And now the pendulum is swinging again with the advent of multimodal models, right? We're doing a lot more work with images, with video, 4K, 8K, audio files, what have you. So what's been clear to us is that infrastructure for AI is evolving at a much more rapid clip than anything we've ever seen before, right? So it's incumbent on us as providers in this ecosystem to be fungible, to be flexible, to adapt to these evolving needs, and be able to serve them as the technology advances. I mentioned that we've been working with Meta for about 7 years or so right now. Part of why we've been so successful at this large scale is because of the power efficiency and the space efficiency that we're able to bring to bear. I'm going to spend some more time in this talk talking to you about how we deal with media from the ground up. We buy raw NAND chips, we put them together. We don't use commodity SSDs, and there's a science behind why we do it this way. So we'll spend some time talking through that. But that enables these massively power efficient, space efficient solutions. And why is that important for AI, you ask? Well, it's because for AI, your primary currency is keeping GPUs fed, right? GPUs, as we know, they're extremely power hungry. They consume a lot of space and lots of power. So the more efficient the surrounding infrastructure is, the more resources, be it space, be it power, be it cooling, you have to devote to the workhorses that are the GPUs. From a storage layer, as we look at AI, it isn't just one thing, right? I know we're all tempted to think of AI as pictures of your cat running on top of a monkey or the Pope in a puffer jacket, but really from an infrastructure perspective, it's way more than that, right? It's being involved in every step of the data journey. So we see that right from ingestion of data. So if you're sitting on a factory floor, you have tons of images phoning home, you have images calling in, you're trying to make on-the-fly decisions based on the images that you receive. All of that has to land on some storage appliance, right? And from then on, you go to the next phase where you're doing some processing on the data that's landed. Maybe you're curating it, you're labeling it. There's a bunch of pre-processing that you do. And then you move on as a company, you have multiple choices as to what you choose to do with that. Maybe you're building a foundational model, right? So then you have tons of this training gear that's set up, and your storage needs to be able to feed your data into that. Or maybe you're taking a pre-trained model and you're trying to fine-tune it based on some of the data that you've collected. Or maybe you're performing another application like RAG, retrieval augmented generation, where your data really is your secret sauce. You're taking a pre-trained model and you're trying to fine-tune it. You're trying to adapt it to the needs of your vertical based on the proprietary data that you have. So all of this is happening on the infrastructure, sometimes simultaneously. And as you can see, the needs from a storage perspective are extremely varied. So the ideal storage system, as we see it, is really more than just servicing reads at peak bandwidth to GPUs. It's participating in this entire pipeline, performing all of these operations simultaneously. Right? So this is how we think about performance. Performance really is multidimensional, right? Because at the end of the day, you're striving to deliver outcomes to your data scientists within seconds, minutes, hours, instead of weeks, months, or years. So from an infrastructure perspective, we're looking to handle a multitude of operations simultaneously, like I said. You're handling large or small files. You're doing reads of them concurrently with doing writes as you're handling ingestion. Really large training jobs take a checkpoints. Now, checkpoints have become extremely important in the recent year or so, given the size of these foundational models, the scale at which they're running, and quite honestly, the frequency with which parts of the infrastructure fail, like GPUs do fail. So that's the reason why these checkpoints are taken as often as they are, and they get persisted. In certain verticals, these checkpoints are extremely important to track provenance of results. Like, why did your car swerve left at this particular sign? Well, you got to trace that back, and for that, you need to maintain all of the flows that got you over there. Right? So checkpoints are extremely important to AI workloads. Now, checkpoints tend to be extremely bursty. They need extremely high performance for a short period of time. And the reason that they're so important to get out of the GPU's way is you don't want to block your GPU on trying to spit out some contents from HBM. You want your GPU back chugging on the next set, the next iteration. So from an infrastructure perspective, we're trying to handle all of these simultaneously. We're dealing with low latency ops, random accesses, sequential accesses, etc. So wearing our enterprise hats, and having built enterprise-grade storage solutions for the last 15 years now. By the way, we're just celebrating our 15th anniversary this week. We skipped out on our anniversary lunch to come and hang out with you all.
Happy birthday.
Yeah, thank you. So the things that we've learned from the enterprise are all about high degrees of resiliency, availability, and predictability. So performance needs to be predictable. It's oftentimes far more important to deliver predictable performance than peak burst performance that tapers off under duress, right? At scale or under failures, etc. Predictability, seamless, granular expansion is extremely important. Performance has to be delivered from our vantage point without complexity. So no nerd knobs, no tuning. The storage systems, to be truly enterprise grade and bring the power of AI to the enterprise, need to be able to adapt to the changing circumstances, but without complex tuning, right? The interesting thing with AI is we're moving from the land of HPC, where there were science experiments. That's kind of how we got started, to the mainline enterprise, where the IT teams and the teams that interact with these systems need more predictability and conformity with the rest of their infrastructure. I've mentioned now a couple times about power efficiency, and really that is the name of the game from an storage appliance perspective, right? How do you create more headroom for GPUs? And that can be done via delivering extremely power efficient storage infrastructure. And finally, flexibility, as I've mentioned now a couple times, to be able to adapt to the rapid change of pace that we're seeing. So distilling this down to a few key principles, from a platform perspective, we see the need for high performance, extreme efficiency, simplicity and ease of management, high degree of reliability, and extreme flexibility as sort of being the cornerstones for delivering AI and for bringing AI, for democratizing AI, for bringing AI to the masses. So you'll see this motif throughout all of our presentations. We'll keep hitting on different facets of our product and how we focus on these 5 pillars and bring them together when you look at our real world solutions. All right. So the product that excuse me, the product that we participate with in all of our AI opportunities is FlashBlade, as I've mentioned. FlashBlade delivers performance and power efficiency for all AI workloads. It is a scale-out, all-flash file and object platform. As a quick primer, Pure provides a unified storage environment that satisfies the needs of all of the data center. Underpinning that are 2 hardware architectures. There's FlashArray, which is a scale-up product that is built for low latency, and then FlashBlade, which is a scale-out product that is built for high degrees of concurrency and throughput, which is what you see for AI. I mentioned before that we don't use commodity SSDs. Instead, we choose to build our own SSD equivalents that we call DirectFlash module. And we'll get to why we do that and what that enables in a couple slides. So FlashBlade checks all the boxes that I mentioned previously. We provide high performance, standards-based file and object access. And we think that is critical to getting AI into the enterprise. The fact that it's standards-based, it's your standard NFS client or standard S3 client, standard SMB, and the customer does not have to manage custom clients or deal with custom distributions to get their storage system up and running, right? It's architected for high performance across the multitude of applications that we see, across multiple dimensions, high emphasis given to metadata, write performance, small file streaming, and the ability to handle all of this concurrently. Pure's unique selling proposition, or USP, is our DirectFlash technology. That underpins all the products that we build. It allows us to provide huge power and space efficiencies over commodity SSDs. For reference, we recently announced a 150 terabyte SSD equivalent, and we can ship up to 40 of these within a single chassis. So when you multiply that out within a single standard 42U rack, we're looking at 40 petabytes worth of usable storage. We'll spend some more time talking about this, but I want to get that context over just so you realize the level of consolidation that we're able to drive on all of the storage infrastructure, which opens up all that much more space for your AI training. FlashBlade is extremely simple to manage. One of our key tenets was that all the instructions to manage a Pure product should be able to fit on the back of a business card. We're still there 15 years into our journey. Everything is extremely simple. If you go back to networking, we've simplified what would traditionally be 3 different networks, a front-end, back-end, and management network, into one single high-performance Ethernet fabric, all managed via software-defined networking. And Boris will spend some more time talking about that in his future section.
So, I had one question.
Yeah.
So your object and file is on top of object, or how is it, like in terms of architecture?
Right, great question. So file and object are native. So file doesn't sit on top of object.
Okay.
Really, the way we're architected is as a distributed key value store underneath. So we separate the Pure software at its heart is really a giant distributed key value database. And then we open up protocols on top of that. So every protocol gets the full performance of the infrastructure.
Okay. So there is no layering of protocols. It's
Correct.
Independently layered at a single level.
Correct.
And underneath, it's a distributed key value store.
That is correct.
Got it.
Yeah. Great question. Was there a follow-on?
No,
okay,
thanks.
Our DFM technology, or DirectFlash technology, is key to being able to deliver extremely high degrees of reliability. We've measured our reliability to be over 5x that of commodity SSDs. Now that matters a ton, because when you're looking to deploy AI applications at scale, and we see customers that are building out AI farms with hundreds, thousands of petabytes of storage, minimizing the number of failures reduces the amount of over-provisioning that you might have otherwise had to do with, say, SSDs or hard drives, and it also keeps your GPUs fed longer. Again, coming back to this common motif of maximize the resources you're giving your GPUs, maximize the power budget, maximize the time that they can stay on, and remove all other hurdles from the way. And finally, our architecture is extremely flexible. We have a simple granular scaling model. You scale via addition of a single unit called a blade. That's the cutout that you see on the graphic up here. You can add individual drives to the blades. You can add individual blades. So it's an extremely granular scaling model. And that allows us to pick optimization points across the entire price, performance, cost, power spectrum to tailor it towards the customer's needs. And Evergreen is a philosophy that we've adopted. So the notion behind Evergreen is the ability to keep the array running and perform all upgrades, hardware and software, non-disruptively. We actually have customers who've been running on Pure technology for over 10 years. We've migrated them from, I'd say, we migrated them across maybe 3 or 4 generations of hardware and multiple generations of software without ever taking the downtime. So our mental model really is that the data is the array. We're able to keep the plane flying and change everything about it, like even change the engine. We're changing out the media. Everything can adapt to more modern technology while keeping the plane still in the air. And that is really unique to this industry. Okay, so I promised that we'd go a little deeper and we'll talk about how we handle Flash and how that enables some of these key attributes for AI. So I have up here a picture of our DirectFlash module. That's the SSD equivalent that we build. And this is core to us being able to deliver extremely high reliability, space and power efficiency, extreme density, and then performance, of course. So let's walk through each of these in turn. Okay, first and foremost, reliability. My previous point keeps the GPUs fed longer. So over here, I have a picture that tracks annual return rates from the industry. You see I have hard drives, SSDs, and then I'll get to the other 2 bars. So for hard drives, it's pretty well documented that about 3 years into a hard drive's life, the failure rates just take off. So over here, I'm showing really the honeymoon period for them, the best point in their lives. This data is backed by numerous industry sources. The citations are listed below. Hard drives failed roughly at about 1.4, 1.5% at the best of times. This is the number of percent of the modules that fail per year. With SSDs, we see that the modules fail at about 1% per year. So when Pure started 15 years ago, we hadn't yet productized our DirectFlash module, so we were using commodity SSDs. We did a bunch of software work to try to work around what was happening within an SSD, and we were able to bring the failure rates down a little bit, about to say 0.8% or so. And you can see that with DirectFlash modules, the failure rates are significantly lower. Now, why is this? It's really because of the simplicity that we drive. This isn't a knock on SSDs. Like SSD manufacturers really, really have a hard job because they have to build an SSD that needs to go into multiple different applications. They don't really have a sense for what those applications are. So an SSD has to perform a ton of tasks, such as managing all of the flash. There's a process called wear leveling to ensure that the flash is uniformly written to, manage the life cycle of a flash, manage garbage collection. All of that stuff has to happen, but completely opaque to the application. The fundamental science behind DirectFlash is performing the software and hardware tasks needed to keep Flash alive at the appropriate layer of abstraction. So what we do is we hoist a function such as garbage collection, such as wear leveling, such as Flash management. We do that at the global level. So we do that at the array level within our operating system. So if you think at the size of these installations, we're doing this at 10 petabytes, at 100 petabytes, at that scale, rather than do it that at a single SSD. So that allows us to make globally good optimizations in lieu of maybe local minimas that are unaware of what the application as a whole is looking to do. So that simplicity reduces the burden on the SSD equivalents. And that's a fundamental reason as to why we're able to drive down the complexity of these devices and in turn boost their reliability. So as I show over here, each of our modules are about 5 to 7x the reliability of an SSD on a module basis. But I've also now mentioned that our modules are much larger than SSDs. So if you think about this from a per bit basis, which, yeah, if you're installing 100 petabytes of something, ultimately that breaks down into X modules of Y capacity each. On a per bit basis, we're about 10 to 25 times the reliability. And that is driven by the simplicity. The other cool thing is that the failure rate does not depend upon the capacity of the module. So our 10 terabyte module, say, would have the same failure rate as a 300 terabyte module because we don't fail things because the capacity goes up.
So to that end, and we had a little bit of this discussion on the failure rates of HDD versus SSD. previously. One of the things that we see the enterprise struggling with to a certain extent is extending the life of, the depreciation schedule.
Right.
Going from 5 years to 7 years, we're only seeing a little bit of that adopt.
Mm-hmm.
And now you're talking about 10 years?
In
maybe
certain cases, yes.
In certain cases with this DirectFlash.
Correct.
That's a long time.
Well, it is. It is. And so that requires us to make extremely judicious use of all of the wear that we're putting on the drive. So that's a great thought. And I actually have a slide that addresses the key reason why we're able to do that.
Okay, there's one key reason to doing it, but the adoption of that, which is also the people, procedures that the enterprises have on there, changing their mind, how they look at this.
Yeah. Well, I guess I would say that the modules are one component of a larger system.
Yeah.
So
okay.
At Pure, we offer an evergreen business model to customers that allows them to upgrade their controllers as newer CPUs or newer network cards come about. That's our promise, to keep them on the most current technology. But when we do that, because of our investment in DirectFlash, we don't need to go and replace the drives at that same cadence. The drives could last much longer as long as the surrounding bits are replaced to get them onto the more modern technologies.
Okay.
Question. You just said you have a 10 terabyte module and a 300 terabyte module, and the chance is as high or as low for a failure, but you have more chips, more components if you want to store 300 terabyte.
Yeah.
How do you explain that probability is the same?
Yeah, that's a great question. So
it's not logic, at least. So
correct. Yeah. So it's a great question. So why do I claim that the module failure rates are the same? Well, that's because chips might fail, right? I think you'll have individual cells of NAND that fail, individual the way to think about Flash is it's really a stacked Russian doll type of architecture. Like within a chip, there are die. Within a die, there are planes, there are blocks, there are pages, there are cells, etc. So anything could fail at any layer of that abstraction, and we do a ton of science studying those failure rates and characterizing them. If an individual component were to fail, like if a die were to fail, we wouldn't have to replace the entire 300 terabyte module. Like we would using our technology, we're able to paper over that, and we're able to use the remainder of the drive. So we're basically abstracting away failures, and the only reason we have to return drives is if a non-NAND component fails, or if there's a catastrophic failure to the NAND chips themselves and you fail above a certain rate.
But then at that moment, the over-provisioning for the garbage collection will be higher for a 300 terabyte module then.
So that's my slide over here, where we have no over-provisioning. Again, this is the reason why we handle things at the array level. I'm less concerned about whether a single drive has failed maybe 0.01% of its capacity, because when I'm managing 1,000 drives at the array level, I can balance it out with another drive that hasn't failed anything else and has a little excess capacity available.
But so you're moving data around then?
We might have, yes, because in the event of a failure, all of the data that's stored on our arrays is erasure coded across drives. So if an individual stripe of that erasure code were to fail, well, we would rewrite that segment somewhere to get back to full parity, to get back to the full erasure code. So yes, in that case, we are moving the data, but we can do this at a global level rather than within the SSD level. But that is a great segue to my next slide, which is why we're able to drive this density. I have a cartoon of a standard SSD on the left, and an SSD has two things. You brought up over-provisioning. Over-provisioning is the act of setting aside some capacity to handle a mismatch between the way Linux or your standard block device driver would program the flash, say that's at 4 kilobyte chunks, to the native NAND geometry. Like NAND wants to be written at maybe 16K or 128K, and that changes every generation. So how do you do that? Well, the answer is you have to have a bounce buffer, and that is the over-provisioned part of the flash. On a standard SSD, that's about 20% of your bits. Second piece of inefficiency is an indirection table. Because remember, what we've effectively done with the bounce buffer is we've added pointers, and you need a pointer management structure that is an indirection table. That typically lives in DRAM and is typically sized at a gigabyte of storage, the gigabyte of DRAM for every terabyte of storage. Think about that. I just mentioned we do 150, 300 terabyte drives. We have 300 terabyte drives in the offing. At that capacity, you're delivering more DRAM than exists in a server, right? So with that, compound your failure rates, compound your costs, compound your inefficiencies. To contrast, I've shown a picture of the Pure drives on the right. We have no over-provisioning because we're handling all of the writes to the flash at native flash geometries, because we're able to do this at the array level. This also allows us to get rid of all of this excess DRAM that's required for mapping, because we're maintaining all of this at the global level. So in both of those together, eliminating all of these drive level mappings allow us to drop our DRAM versus a drive by more than 40x, and then gain 20% more capacity per drive with the same number of chips. Both of those together drive our density. They allow us to build these much larger drives because we aren't handicapped by needing to throw a bunch of DRAM onto them. So as you see from the graphic above, I announced that we ship 75 terabyte drives today. We've announced 150 terabytes, which we will start shipping in a couple months. And then we have designs on a 300 terabyte drive that will ship in the next 15-ish months or so. This density is enabled by our investments in DirectFlash and by removing all of these unnecessary inefficiencies that exist on a standard SSD.
Can you elaborate more on how less DRAM is used, like 40x less? How's that happening?
Yeah. So if you remember the discussion on the previous slide, we mentioned that there is a mapping table that manages all the indirection within an SSD.
Right.
And that scales on a standard SSD at about a gigabyte of storage for every terabyte.
But that's inside the drive, right?
That is inside the drive, correct.
Right.
But then if I am buying 100 petabytes worth of storage, I'm throwing that much more DRAM per drive. On a Pure solution, we don't have that DRAM within the drives.
Oh, so this is DRAM within the drive that we are talking
Correct.
about, and
Yes.
not in the server.
Correct. Yes. Yeah. So specifically, we're talking about all the excess DRAM that needs to get added to SSDs
Okay.
to handle all of these mappings and provide the right level of performance.
Okay.
Versus with the Pure DFMs, how we don't have to use that DRAM.
And if you use Pure DFM, then also you would need some form of mapping, right? It's like you have unboxed individual modules outside the boxes, and they would still be mapped. The pages would still map to the logical addresses, so the mapping would still be there.
Correct. But in either case, the operating system is always maintaining some mapping. The operating system always maintains a level of indirection, because the operating system that sits above an SSD or a Pure drive is dictating what goes where and managing all of those structures. So we're able to consolidate onto that single data structure instead of having multiple layers that manage their own individual indirection.
Okay.
That makes sense.
Okay.
Now, I see that you're using QLC there. Are we going to take a look at performance, because QLC is lower performance compared to TLC?
That's a great segue to my next slide. So yes, QLC is considered to be lower performance, but we're able to enable, on our FlashBlade product, we enable the highest levels of performance for AI with QLC media. Part of how we can do that, again, no prizes for guessing, is through DirectFlash. The idea with DirectFlash is we provide our software with controls down to the individual NAND die level. So it's our operating system as a whole that is managing scheduling of operations. Part of what makes scheduling complex on an SSD is that the flash controller on an SSD has to perform background operations like garbage collection, and it doesn't know what's going on. So it could have scheduled a high latency operation. We can be extremely surgical about how we schedule operations because we know what's happening at the array. The other reason is because with DirectFlash, we reduce the amount of background operations. So if you remember from my previous slide, we spoke about over-provisioning and how that in turn results in multiple copying operations within the data, right? Because you've over-provisioned it, you have to copy that back to a Flash native geometry. All of that triggers multiple background operations within the drive, and it puts more wear on the drive. To your earlier question about how we get more life cycle out of it. Turns out that with QLC, even though the write latencies are longer, there are far fewer program erase cycles than are available, say, with TLC or MLC, etc. So we have to be extremely surgical in how we utilize those cycles. And we're able to do that by reducing all of the background tasks. So a write to flash is in effect a final formed write and doesn't need to get rewritten 2 or 3 times. That's typically referred to as a write amplification factor. And the SSD industry tracks that pretty closely. On Pure systems, the write amplification factor is extremely low. Like most of the writes are only because of mainline operations or an occasional garbage collection when a ton of data churn happens.
So what's the page size of individual like flash modules that you're working with? 16K?
I'd say 16K is a fairly common size.
Okay.
When you look at technologies like QLC, oftentimes you have to program multiple cells together. And then sometimes you have to program multiple planes together. So the size of a program could be 16 or 64 or 128.
Okay. And what kind of optimizations do you do for small files, a lot of small files?
Yeah, so it's a great question. So that leads into my next question. So how do we handle small files and metadata? Well, again, so we have a small cache, if you will, a small amount of DRAM that handles writes as they get ingested. That allows us to acknowledge the client immediately.
Okay.
Right? But ultimately, that cache needs to be drained, and it can only be drained to persistent media as fast as the flash media is able to go. So our investments in DirectFlash allow us to perform writes really quickly, which allow us to handle small files or small metadata. Other approaches to this that we've seen involve tiers, right? So there would be alternative media sources that serve as a tier into which metadata or small files would be written. The challenge with that approach is that that doesn't scale, because a cache needs to grow with performance and not with capacity. You have to be able to decouple growing capacity versus the performance that you're driving. The disadvantage with a tiered approach is that that has to grow as you add capacity. So ultimately, our approach allows us to get more optimizations at the system level because we're more efficient. We can grow capacity independent of the need to grow performance.
So do you guys also pack small files into a single page?
Yes.
So that page is properly utilized in terms of space consumption?
Correct. Yeah. So we have multiple algorithms that balance how long buffers stay open versus packing them efficiently. And this, again, we do this at a global level. So we're not constrained like an SSD at having to do this at, hey, these are my small writes that landed on this particular drive. We're looking at a much more global scale, so we can be much more optimized in the way we pack stuff together. Great questions. Thanks. So with that, I'll just pop back up the stack a moment as my last slide and then lead off to the next section, which for those of you online, I do invite you to listen in on. This architectural rigor that we apply to handling DirectFlash ultimately is what enables all of the goodness that I mentioned to you around FlashBlade, which is ultimately resonant in customer wins that we've had, and also a bunch of work that we're doing in the AI ecosystem with our AI partners. We recently announced with NVIDIA that we're going to be part of their SuperPod architecture, and we're on course to completing that certification towards the end of this year. We have multiple reference architectures with NVIDIA, a few pictures of which we show on here. And the third segment of this talk has Robert covering some of these in more detail.